Hello everyone. We are now back with the second part of our series on modular arithmetic, where we will bring up some of the famous theorems by Euler and Fermat and some others which we are going to see. Now, before we do that, let's do a quick recap as well as look at some of the things that we can already do without the help of Euler's theorem, Fermat's little theorem, and all the other stuff. So in order to know when to use a theorem, we also need to know why the theorem exists. We also need to know when we do not use the theorem. So we do not need to use the theorems here, or rather we don't need to use any new theorems here on this problem. Now this problem asks you to find the remainder of x when divided by 2020. And so the theorem that we can use at this point is the Chinese Remainder Theorem, if you recall from what we have said in the previous video. The Chinese Remainder Theorem tells you that you can chop this up into smaller bits. So you can divide 2 squared times 5 times 101 into 2 squared, 5 and 101. You don't have to divide it all the way into smaller bits, you can just use 20 and 101. Now when I want to divide mod 20, x is clearly going to just depend on its last 2 digits, and the last 2 digits are just 1, so that is straightforward. As for the mod 101, what we can do, as suggested in the previous video, is we can chop this up into 2-digit blocks. So I'm writing this from right to left. And this goes all the way until my 2-digit block of the 2-digit number 10. The 2-digit number 10, which is the 72nd number, so that 100 to the power of 71. Followed by the rest of them, which would be just the single digit numbers, which I can also divide into blocks like this. So 72, 73, 74, 75, 76. Oops, my face is blocking this, isn't it? Okay, so now that we have this, our trick when we did mod 101, and really at the heart of our modular arithmetic in the first video, is that we are able to replace any of the numbers by a suitable representative. And so I can use -1 instead of 100. Oops, I realized that this should be 100, not 10. Change that. Again, I'm dividing off this part as being different because the front part is simply going to be 81 minus 80 plus 79 minus 78 and so on. And the back part is going to not move that way, it will move like that, so it's probably a good idea to just write them down explicitly. Okay, each of these pairs is 1. There is 22, 22, and there's 1. So 10 to 81 has 72 numbers. So 72 divided by 2 ones, a 22, a 22, and a 1. So 36 plus 22 plus 22 plus 1 is 81. So 81 mod 101 and 1 mod 20, which conveniently enough already works as 81 is 1 mod 20. So this is going to be my answer. This we can do with the help of our Chinese Remainder Theorem, and just as importantly, we do not need to use any high-powered theorems. Now, as you've seen here, we talked about divisibility test as well. Divisibility test, either we can use it to justify those that we know, or we can use it on things like mod 101 that we are hoping to discover something a bit different. So for our second example from the SMO senior, we will see how this can also apply. So here we are told that we want A to be the digit sum of this, B to be the digit sum of that, and then find the digit sum of B. This at first glance seems like a very difficult question, because 2020 to the power of 2021 is very big. But before I do anything else, let me just think about how big is actually the digit sum of 2020 to the 2021, and the digit sum of that, and the digit sum of that. Is it really that big? Well, the answer is surprisingly no. And to explain why, I'm going to use the worst estimate you have probably ever seen, which is that 2020 to the power of 2021 is less than 10,000 to the power of 2021. This does not sound like a very good estimate. Well, I'm going to make it worse because this is 10 to the power of 8084. I'm just going to say that this is less than 10 to the power of 10,000. That just means that it is at most 10,000 digits. It does not sound like a very smart thing that we are saying, but you realize that this means that my A is less than 9 times of this, which is very small, at least compared to what we thought it might be. Now this is already a terrible estimate, but it means that from this big number, A is just at most a 5-digit number. And therefore B is at most 5/9 in terms of its sum, which is 45. And so I should bear in mind that the digit sum of B is very small. This is the first thing. The second thing is, where else have we seen digit sum before? And the answer to that in a modular arithmetic video is quite clear. We have seen this being mentioned as the test for 9. In other words, what I'm saying here is that 2020 to the power of 2021 is congruent to A, which is congruent to B, which is congruent to my answer, mod 9. And B is small, the answer is even smaller, so therefore that would give me good hope that if I know what 2020 to the 2021 is mod 9, I should be able to make that happen. So 2020 to the power of 2021 mod 9, we know that 2020 is congruent to 4 mod 9, and so we have talked about this last time. How am I supposed to find the remainder when some big power is divided by 9 or by anything else? And the answer is that because 4 and 9 are small, I can just find a pattern of powers of 4 modulo 9. So it starts with 4, 16, which is 7 mod 9, 7 times 4 is 28, which is 1 mod 9, and it repeats after that. So it repeats after only 3 steps, and therefore since 2021 the exponent is congruent to 2 mod 3, it will be the second thing in the pattern. So straight away we have found that my answer is congruent to 7 mod 9, and I know that the digit sum is less than, the biggest possible thing you can get is 3 plus 9, which is 12. And so if it is 7 mod 9 and the digit sum is less than 12, your answer is really 7. So this is divisibility test meets modular arithmetic, and the modular arithmetic that we're using on the power just required us to find a pattern. So 4 to the power of 2021 did not require us to use any theorems as well, because this is small. And we can list the pattern now. Now you can start to imagine why this may be a problem. This may be a problem if I have got bigger numbers to work with. So for example, if you were to look at this question from the SMO Senior 2023, we are asked for the smallest positive odd integer greater than 1 that is a factor of this. And if you were to think about, oh no, what if it turns out the factor is something like, I don't know, What if the factor is something like 2025 or 2027 or something very big? Then how am I going to handle this big calculation? Well, one thing that we can hope for, of course, is that since modulo something big is hard, we can use wishful thinking. Is the answer small? And how small? Well, let's try 3. If you look at these, you will realize, much to our delight as well as mild amusement, that 2023 is congruent to 1 mod 3. And therefore, so is 2026, and so is 2029. And so the answer is 3. That's good for us. But it still doesn't answer the question of what would happen if we really have to divide by something big. Now, I've pushed this for some time, 10 minutes or so into the video, because do not use the theorems you're going to introduce on every question. You don't need it for every question, and what we have discussed in the first video already can solve a fair number of questions. However, we also cannot just rely on what we have mentioned on the previous video, because there are times where it will no longer work. And so if we were to look at an example like this, which I'm not going to explain yet, or we look at an example like this, which also I'm not going to explain yet, it suffices to say that we would be in some trouble if, let's say, that we are handling dividing by something big. So for example, if we are dividing by 215, you can say, alright, I split into 5 times 43 by the Chinese Remainder Theorem. But if I now say 3 to the power of something mod 43, how long is this going to take? Let's see. 3, 9, 27, then 81. 81 is congruent to -5, so -15, -45, which becomes -2, -6, -18, -54, which becomes -11, -33, which becomes 10. Now I'm just trying to use numbers that are nice, but this is not going very well. Well, I mean, it is going somewhere, and the somewhere is that it is just going and going and going. 108 is congruent to 22. 22 times 3 is 66. That's congruent to 23. How long is this going to take? Now this is very distressing, because if we just keep listing, what if this goes on forever? Right now, we did not really worry about that previously because, well, it was, let's say, mod 9. How bad can it be? It can't be that bad, because the only things that can possibly show up here are up to 9. Assuming that we are using positives, it's just a very small list of things that could appear. So what could appear is that, well, 1 could appear, 2 could appear, 3 can't appear because it can't be 3 mod 9. That would have been a multiple of 3. But in the worst case scenario, I know that I only really had these 6 things that can appear. And so it really would take at most 6 steps. So if it takes at most 6 steps, I'm willing to take the risk because it's a very small risk. Unfortunately, over here, mod 43 means that everything from 1 to 43 could appear. Now I know that once the same number appears again, it will repeat, right? So if let's say you see a 9 here and somewhere later you see a 9 again, I know that 27 will come next and it will repeat. But how long is that going to take? Potentially 42 steps later. And this is quite sad. Now that's where Fermat comes in. Now, Fermat's little theorem, FLT for short, not to be confused with Fermat's last theorem, Fermat's little theorem is basically going to tell you that, you know what, it will be that 3 to the power of 42 is 1 mod 43. And more generally, what does Fermat's little theorem say? It says that if you are dividing by a prime, then a to the power of p minus 1 is going to be 1 mod p, where a is not 0 mod p. So if a is not a multiple of your prime number, then it tells you that, well, potentially p minus 1 steps later, potentially 42 steps later for mod 43, it will repeat. Well, I'm telling you it does. I'm not telling you, I'm telling you that Fermat's telling you that it does. Now, Fermat is telling us that this is a checkpoint. Now, it is a guaranteed checkpoint. It is not the first necessarily. Now, this is important to distinguish, that it is not necessarily the first checkpoint, because, for example, Fermat's little theorem will tell you that if I'm doing mod 7, 2 to the power of 6 is 1 mod 7, which is true. This is 64, and 64 is 1 mod 7. But also, 2 cubed is 8 is also 1 mod 7. So Fermat's little theorem is not telling you the first place where this happens. It's just telling you a place that this happens. And that's already not bad. You can think of this as bird in hand is worth 2 in the bush. You would rather have something that is going to work. Because if now I were to look at this question, I could say that, okay, what is 2023 divided by 42? I should have probably calculated this in advance. It is 48, remainder 7. So it means that straight away, this guy, the 7th guy, in a sequence of 42, even though I don't know that maybe it repeated after 14 steps. No, it didn't repeat after 14 steps. I wrote 16. Maybe it repeats after 21 steps. But I do know that the actual length is a factor of this. Now, this actual cycle length is also known as order, which, if I'm able to, will come in maybe the 4th or 5th video on this series of modular arithmetic. So we'll talk more about order when we get there, but for now, the focus is on this guaranteed checkpoint at p minus 1. So I'm able to say straight away that 3 to the 2023 is congruent to 3 to the 7, which is negative 6 mod 43. Now, of course, it also applies to things like 5, right? It's also true that 3 to the power of 4 is congruent to 1 mod 5, and that the cycle length is 5, and so you can say that 3 to the 2023 is congruent to 3 cubed, which is 27, which is congruent to 2 mod 5. Now, we didn't really need to use Fermat's little theorem for that, because the pattern really repeats after 4 steps. But hey, I have it, so why not? And so after you have got these, you just put it together. So minus 6 mod 43, I add on 43, I get 37, and that's where I can stop, because 37 is also 2 modulo 5. So you realize that this is quite well, powerful theorem, no pun intended, because it allows you to push down the powers a lot. But what then does it do for something like, let's say, 64, which is not prime? So 64 is not a prime number. How then am I supposed to handle those modulos? Surely, I would like to think that Fermat would have told me something. Well, one option is that if let's say that you were doing it here, you can get clever. So you can get clever by using the binomial theorem. Now you can get clever by using the binomial theorem because many of the terms are all going to now be powers of 8 which are divisible by 64. So you only would need to handle the last two terms of each of these. These cancel off, and so you really just have got 2 times 8 times 20, 23 mod 64, which would reduce to 48. So there are exceptions when we are using modular arithmetic on non-primes. But there's already been an eye towards how this will work when I mentioned the what could appear in the mod 9 example just now. Basically, what's in the list of the what could appear? Well, if let's say that I'm looking at powers of A mod n, where A and n are co-prime. So if let's say that I'm looking at powers of A and n where A and n are not co-prime, that will be a totally different issue. For example, powers of 3 mod 9 will just give you 3, 0, 0, 0, 0, 0, 0, 0. So that's not the kind of thing we're focusing on. If I've got powers of A mod n, basically what I'm saying is that they are still co-prime to n, right? A common factor does not show up. And so the list of possibilities is going to be all the things from 1 to n which are co-prime to n. Now, how long is this list? Well, this is where our semi-famous Euler's totient function, also known as Euler's phi function, this is the Greek letter phi, let's give Euler his due accreditation. It is Euler's phi function slash totient function. This is basically the number of values from 1 to n which are co-prime to n, and what Euler's theorem says is consistent with Fermat's little theorem. But now in general it says that phi of n is the length of the list at most. Here's a guaranteed checkpoint. If your A and n are co-prime. So Euler's theorem says this. And in the case where n is prime, this is actually just Fermat's little theorem. They are the same thing. But Euler's theorem also deals with the non-integer situations. Okay, now some of us would then be wondering, okay, but what is the use when phi of n sounds really complicated, right? So what is, let's say, phi of 2024? I can't list that, can I? Well, thankfully for us, Euler's theorem is not useless because the phi function is not hard to calculate. Now, the phi of a number is calculated in 2 steps. Step 1, factorize. And when I say factorize, I mean prime factorize. So for example, we are still in the year 2024, so in the dying moments of the year 2024, let us factorize it again. Now, step 2 is to say that how many numbers are there going to be that don't have the factor of 2, 11, and 23, or don't have any of the prime factors for my respective number. Well, for each prime factor p, multiply 1 minus 1 over p. So for example, that means that my phi of 2024 is 1 minus half, 1 minus 1 over 11, 1 minus 1 over 23 times of 2024. Now this will always be an integer, right? Because you're dividing off by its prime factor, so it's not really going to be a problem. You will just have all of this cancels off in our case and leaves us with 2 squared, which is 880. So phi of 2024 is 880, which now means that I could say that, for example, 3 to the power of 880 is 1 mod 2024. I could say that 45 to the power of 880 is 1 mod 2024. Of course, as you guys already would probably have realized, I chose 45 for a reason, which is that 45 squared itself is 1 mod 2024. So again, this is just a checkpoint. It may not be the best checkpoint, it's just a checkpoint. But it's better than working with nothing. Now, in the previous video, we saw the example of 2024 to the power of 2024 and its last 2 digits being very easy to extract, because mod 4 is 0 and mod 25, 2024 is just negative 1. But yeah, this would combine to 76 as the last 2 digits. How about if we had some other number instead? So let's go for something like, let's say 2023. For obvious reasons, I'm not going to go for 2025 because that's even easier than what we had last time. So what happens if I want the last 2 digits of 2023 to the power of 2023 instead? Well, if I wanted this and I tried the same strategy, the mod 4 is easy. It's negative 1. The mod 25, however, would hit a roadblock because 2023, the best you can reduce it to is negative 2, which, of course, you can take out the negative. But then what is 2 to the power of 2023? Mod 25. Well, Euler's theorem is going to tell us that 2 to the power of phi of 25 is 1 mod 25. What's phi of 25? Well, 25 is 5 squared. So it is 4/5 of 25, which is 20. Now that means that the cycle length is a factor of 20, and at least I know that 20 is my checkpoint. Therefore, 2023, I can just reduce it down to 3 because 2020 is a multiple of 20. I can say that this is negative 8. And put these two together, if you list out the things that are negative 8 mod 25, you will get 17, 42, and then 67, which is going to be here, right? Funnily enough, the reverse of 76. That's just a random coincidence, nothing there. To help you remember how Euler's theorem works, we can say that this is kind of like a probability. which is that if I pick a random number from 1 to 2024, the chance that it is not divisible by 2 is 1/2. The chance that it is not divisible by 11 is 10 over 11, and the chance that it is not divisible by 23 is 1 over 23, and these are, not too surprisingly, independent events. For those of you who have a bit more insight into the fact that this is not trivial, you are right. The fact that they are independent events is actually due to the Chinese Remainder Theorem again. But for now, the probability intuition will help us just for the computational aspect of this thing down here. Now, to push this a bit further, we might ask ourselves, what happens if this cycle length is too lousy such that what I'm left with is still very big? So all of our discussion today has been on powers, and we know that powers do not lend themselves to quick calculations. Well, an example would be of, whoops, why is the answer already there? Never mind, it's not going to help. An example would be for this SMO open round 1 question from 2024, from this year, where I am asking you for what prime number divides this expression over here, and specifically the largest one, because like let's say 2 already works. Now for this task here, you would have realized a problem, which is that Fermat's little theorem tells me that a to the p minus 1 is congruent to 1 modulo p. But that means that the cycle length is up to p minus 1. However, these are all p minus 2. So it's kind of like if, let's say, that you have gone to a shop that says that with every $20 spent, you will get this free gift. And then all the items cost $19.99. So that's really annoying because you are just shocked. Well, in the case of the shop, what would you do? Well, you would try to find something that is as close as possible to 1 cent. If you really felt that that free gift is worth something to you, you just try to get a bit over $20. In our case here, however, that isn't very clear how one is going to do that. And so in order to help you to understand this, I am going to do something that is probably to my detriment, but to help us understand, I'm going to just do something like, let's look at a prime number that is not so small. Let's look at powers of 2 mod 11. Okay, now powers of 2 mod 11, we have said that by Fermat's little theorem, the cycle length should be 10. So let's draw a cycle. Right? This may take a while, but it's at most 10. So 5, 10. By the way, this is -1, and -1 is always, if it appears, halfway there, because -1 squared is 1. So let's continue on our journey. Okay, so not a very perfect circle, but you have seen that here are the 10 numbers in my loop. Now, not too surprisingly, they are 1 to 10 in some order. And so this is also 2 to the power of 10. Now, if I wanted 2 to the power of 11, I can go forwards. But if I wanted to go to 2 to the power of 9, can I go backwards? Well, the interesting thing is that, okay, so when you go backwards, right, this goes from 1 to 6. The interesting thing is, if let's say that now I treated it as I go clockwise here is times 2. Now, this is 1 to 6, so let's just try, right? If I go back and I treat it as times 6, 6 times 6 is 36, which is 3 mod 11. 3 times 6 is 18, which is 7 mod 11. 7 times 6 is 42, which is 9 mod 11, you see that this actually works, which means that there is a reverse gear available to us. We can U-turn, and what I'm going to say is that 6 is congruent to 1/2 mod 11. In other words, yes, there are fractions, and you must, of course, also understand that we know fractions in modular arithmetic are a bit iffy, so I have to have a proper understanding of what's actually a fraction. Because 6 is congruent to half seems to be wrong, because we said the meaning of modulo is that the difference is divisible. Well, what's the difference? The difference is 11 over 2. That's kind of divisible, right? But we said there's no such thing as fractions. So is it or is it not divisible by 11? And in that case, isn't it that I could also say that 7 over 3 is divisible by 11, because 7 over 3 divided by 11 is a fraction. 11 over 2 divided by 11 is a fraction. But we kind of know there's some difference. So let's try to clarify this. Now, the first thing is that for sanity's sake, you might want to write it in this way as the inverse. And we would say that 6 is the inverse of 2 mod 11. Now, the meaning of inverse is that their product is 1. That's how fractions work, right? The inverse of 1/7 is 7, the inverse of 7 is 1/7 because they multiply to 1. In the case of modular arithmetic, that means that the inverse is the thing that would multiply it to 1. And so 6 is the inverse of 2 mod 11 basically means that I can actually say that 2 to the power of 9 is congruent to 2 to the power of -1. I can use my cycle length of 10 to actually go into negative exponents as well, not just negative bases as we have seen in the last video. And so if I now dip into the negatives here, I would be able to get fractions, kind of. But you might ask, so how do I find a fraction or an inverse? Now, unlike the ones we have said so far, this is a bit less obvious. We do need to be careful in understanding how this actually works. How do inverses actually work? And so, to start off, a over b, the fraction, or n, means a times the inverse of b mod n. In turn, the inverse means the value x such that xb is 1 mod n. So the inverse has this meaning. Does the inverse always exist? Think about normal division. Can we always divide? Well, yes, in real numbers we can, except for 0. We cannot divide by 0. We cannot divide by 0 because nothing times 0 is 1. So 1 over 0 is saying what number times 0 is 1. 7 over 0 is what number times 0 is 7. Now if I ask you for an inverse, you might say, can I find it all the time? How do I know? Well, the inverse exists. Again, same thing. If and only if it is co-prime to the modulo. So for example, in mod 11, everything is co-prime except for 0 mod 11, so they all have an inverse. If, however, let's say that I'm working in mod 10, I know that 2, 4, 5, 6, 8 all have no inverse. And 1 is its own inverse, 9 is also its own inverse, and 3 and 7 are inverses of each other because 3 times 7 is 1 mod 10. How do I find an inverse? Well, you are allowed to say that a over b is congruent to a plus any multiple of n over b. If your fraction even makes sense. So for example, 1/2 is congruent to 12 over 2 is congruent to 6 mod 11 because 1 and 12 are congruent mod 11 and the base 2 makes sense. So therefore, if let's say that I now have got a 3 over 7 mod 11, I could of course try to find the inverse of 7. I could also just say that, well, let's just keep on going, and in one step we get, 14 over 7. So that's actually going to be 2. I get that it looks funny that 3 over 7 is congruent to 2. But yes, because the base is co-prime to 11, this actually makes sense. Now, the good news about this is that because now I have access to fractions, I can go backwards. So for this question here, after all that's been said, essentially I am claiming that this mod p, assuming that my p is bigger than 7 so that they're all co-prime, I can actually push them all into the world of inverses. And if you're saying that, but it's p, I don't know what is p, how do I find the inverses of all this mod p? You don't need to yet. It is actually just a bunch of fractions. And yes, you can add fractions and subtract fractions and multiply fractions and divide fractions normally in modular arithmetic as well, which is amazing. Both from a wow, that works in math, as well as wow, that's really good for me perspective. If we do a bit of addition, this half 1/3 1/6 is 1, so there is 2. You're left with this, which I do need to add, and this is 761, which you accidentally saw just now, over 280. Now that means that if I want my prime number to be 0, so if I want this to be 0 mod my prime number, this should be a multiple of p. And quick check, or not so quick check, will tell us that 761 is actually prime, and so that's why the answer is 761. Pretty amazing that this is actually permissible. Now the final thing that I would like to say on the topic of inverses is, so what else can I do with this? Now, it actually gives you a pretty good insight into just how all my numbers work in mod n, which is that they kind of pair up. So for example, in the mod 11 just now, 1 times 1 is 1, and 10, which is basically -1 times itself is 1, so they both loop to themselves. Now we have seen already that 2 and 6 are inverses. You can also see 3 times 4 is 12. That's an inverse. Now 5 times 9 is 45, and 7 times 8. So those actually come in pairs. Now, how does this actually work? Well, we can go back to our definition of modular arithmetic to understand why this should not happen. Sorry, no, this should happen, and any alternatives should not happen. Now, assuming that, let's say that I look at mod n, and I'm looking at mod n for stuff where A is coprime. Now I can look at, therefore, at all my candidates, right? So I'm going to look at 1 times A, 2 times A, 3 times A, and so on until n minus 1 times A. These are all the candidates for potentially one of these to be 1 mod n. Let's just put 0 times a for completeness sake. Now what I claim is that these form a complete set of residues mod n. When I say a complete set of residues, I mean literally that they just form 0, 1, 2 to n minus 1 in some order. And the reason is because they can't repeat. If xa is congruent to ya, that means that xa minus ya is congruent to 0, which means that a times x minus y is congruent to 0. But this cannot happen because a has no common factor with n, so it's not helping to make it divisible by n at all. And this is less than n, so it definitely cannot have all the factors of n because it is smaller. Unless x and y are the same. So therefore, everything in this list will be different, and so exactly one of them will be 1 mod n. So they will always have to come in pairs. Now that includes pairing up with itself. Because of that, it means that your fractions really make sense. The fractions really make sense for any of these because you're not like, okay, but isn't it weird if let's say half can also be equal to this, it can also be equal to that, it can be equal to that, like that would be weird. But it turns out that my fractions are actually meaningful, well-defined quantities. And it allows me, as a byproduct, to prove the last theorem I want to mention for today, which is Wilson's theorem. A pretty cool result, which just says that p minus 1 factorial is congruent to negative 1 mod p for all primes p. It's pretty cool because for factorials, we don't really imagine that there would be so much that we can easily say it's either just divisible by the number because it has so many factors, but if it's not divisible, then it has so many numbers. How am I supposed to control anything? But Wilson's theorem tells me that if p is prime, this is going to be minus 1. And by the way, of course, for p being not prime, then if it's not prime, then you will just be able to find its factors in here, so it would just be 0. Why is this the case? Because of the inverses that we just mentioned. So if we just think about the example of p equals to 11, and we just have listed them all out. All of these pairs multiply to 1. So if I multiply all of these together, this is just going to be 1, 1, 1, 1, 1, and then this leftover last guy is minus 1. So the leftover last guy is minus 1. You get basically 4 pairs that give 1. You have a 1 and a minus 1. So the product is minus 1. But how do I know whether some of them are going to pair up with themselves? That's the only trouble, right? Because if they all pair up except 1 and minus 1, I am done. But what if some of them pair with themselves? Is its own inverse. Well, the answer is pretty simple. The answer is that if it is its own inverse, then it literally means that it is multiplied by itself. When it is multiplied by itself, it gives you 1 mod p. Which means that p divides the difference, which is factorizable into n plus 1 and minus 1. And we know that if a prime number divides this, it means that p divides either n plus 1 or p divides n minus 1, which in turn means that n is congruent to 1 or minus 1 mod p. So the only way that something is its own inverse is 1 and minus 1, and it will therefore prove Wilson's theorem, giving us nice, straightforward conclusions for the factorials of things that are 1 of a prime number Like, let's say 10 factorial is now congruent to -1 mod 11. Final thought, as a question, if let's say that now I pick some random big prime, right? So I can tell you that 2027 is prime if my recollection serves me right. What is 2024 factorial mod 2027? And yes, I said 2024. Modular arithmetic is a lot of fun because it gets us to play with numbers in a lot of unexpected ways, and not just by finding patterns. We now have got some tools and some infrastructure to build more useful conclusions for both the general case as well as specific constants. I'll leave you this parting question, and I'll also leave you with advertisement that for the next video we're going to be looking at modular arithmetic as what I call a filter. So we have been using it very computationally so far, but what we want to use modular arithmetic for as a filter next time will be to answer questions like can x cubed plus y cubed be equal to, let's say, like now I'm picking my numbers very wisely, let's say 3, 3, 3, 3. Questions like this are going to be what we will be able to answer if we use modular arithmetic as a filter and as a test. So that is what will come next. If you have any questions, please leave it in the comment section below. This is SMO senior level. What is going to come after is probably still in this vicinity, and we will try to conclude at things that go all the way up to an SMO open level. Right? Modular arithmetic is something that is that rich that it goes all the way through the levels of the SMO. Thanks for watching, and see you again soon for that next video.